Welcome to the deep dive. We take complex topics and really try to boil them down to the key insights for you fast.
That's the plan.
And today, wow, we're going on quite a journey. We're talking centuries here, looking at this really fascinating intersection of, well, old philosophy and brand new tech.
Specifically, artificial intelligence. We're digging into how Gottfried Wilhelm Leibniz, a 17th century philosopher, believe it or not, laid some incredibly important groundwork for AI. Complex groundwork, but profound.
Exactly. We've been looking at excerpts from Leibniz's Universal Calculus and Modern AI by Gerardo and Giovanni Alvani.
Yeah, and drawing on insights from people like Vernon and Furlong, Daskal, Wheeler, Bick, Poli, Vadinsky, Fasiku. Quite a range of perspectives.
Right. So our mission, basically, is to unpack Leibniz's huge vision, see how it influenced early AI maybe in ways you wouldn't expect, understand where it kind of hit its limits, and then see how modern AI is still wrestling with those same challenges, trying to move beyond his original dream. So you're going to get a real shortcut to understanding AI's philosophical roots.
And why some of the big debates today aren't actually new at all. They go way back.
Let's dive in then. So Leibniz's big philosophical dream, this characteristica universalis. Can you maybe paint a picture of that for us? What was this thing supposed to do?
Well, it was incredibly ambitious. Leibniz basically envisioned a system, a language, that could encode all human knowledge, not using, messy everyday words, but a finite set of basic symbols and pure logic.
Okay.
All knowledge.
Yeah. The idea was, if you could do that, you could settle disagreements just by calculation. Like, let us calculate, he famously said, resolve things rationally.
Wow.
And the key thing for us is that this concept, it provided a foundational philosophy for AI, a way to formally encode abstract knowledge so machines could work with it.
So like the ancestor of code.
In a philosophical sense, yes. It set the stage for thinking about knowledge as something representable and manipulable. Vernon and Furlong said his work really set the agenda for symbolic AI, leading to things like the physical symbol system hypothesis. That's amazing. A 17th century idea setting the agenda for AI. But what's the hidden challenge there? Applying these old ideas to modern tech.
That's a really good point. The power is its elegance, this idea of perfect logic. But the trap, perhaps, is that the real world isn't always elegant or perfectly logical, is it?
No, definitely not.
It's messy, it's contextual. And try to fit all that into predefined symbols. Well, that's where the tension comes in. That's the struggle AI inherited.
Right. Okay, so it wasn't just a dream. He had this calculus ratiocinator, a universal calculus.
Yeah.
How did that become more like a practical blueprint?
Exactly. It moved from pure philosophy to a framework. This calculus ratiocinator was essentially the engine for his universal language. And it laid the groundwork for, huge chunks of modern computation.
Like what specifically?
Think Boolean algebra, the true-false logic at the heart of all digital circuits. Think predicate logic, which lets us formalize statements computers can reason about. And even the theoretical basis for Turing machines, the concept of a general-purpose computer.
Okay, so direct lines there.
Absolutely direct. These became the foundations of what we call classical AI systems, using rule-based reasoning on symbols. You see it in expert systems, in formal knowledge bases, where machines use logic to make inferences. It's Leibniz's framework in action, really.
So how did this start showing up in actual, programming?
Yeah.
Were early AI languages built directly on this blueprint?
They really were. Take LISP, for example.
Yeah.
It was almost purpose-built to embody this idea of symbolic reasoning. Code is data. Data is code perfect for manipulating symbols.
Right. I've heard LISP was key for early AI.
Oh, absolutely. And Prolog, too. Prolog lets you basically state facts and rules and logic, and then the system deduces answers. It's very Leibnizian in spirit.
Okay.
And this is the crucial, but even these powerful languages hit a wall pretty quickly. They really struggled with the sheer fuzziness of the real world, its incompleteness, its context sensitivity.
So the universal dream clashed with specific realities.
Exactly. It highlights this core tension we still see. Do you aim for universal rules? Or do you build systems that are super context-specific and adaptive? It's a fundamental design choice.
Which leads perfectly into this physical symbol system hypothesis, doesn't it? That idea seems central to Leibniz's calculus. Can you break that hypothesis down, and where did it stumble?
Precisely. The hypothesis, in simple terms, is that any intelligence, human or artificial, comes down to manipulating physical symbols according to rules. So classical AI tried to build systems that did just that. Represent the world symbolically, apply rules, get intelligent behavior.
Makes sense.
The goal was comprehensive representation and reasoning. But the roadblock, the big problem, was realizing that, well, most real-world stuff just can't be neatly captured by symbolic systems alone.
Like what sort of things?
Think about understanding sarcasm, or recognizing a friend's face in a crowd, or feeling empathy. These things are incredibly hard, maybe impossible, to reduce purely to symbols and formal rules. That limitation really pushed the field forward.
Towards what? What came next?
Towards what are called hybrid cognitive architectures. This was the attempt to kind of bridge that gap you mentioned.
Hybrid, meaning mixing symbols with something else.
Exactly. Combining the rule-based reasoning of symbolic AI with the more adaptive pattern-recognizing abilities of connectionist systems. Think neural networks, basically. Systems that learn from data rather than just following pre-programmed rules.
Okay, so trying to get the best of both worlds.
That's the idea. Take Sun's Clarion architecture. It's designed to do both. You can use explicit rules, but it also has a connectionist part that learns and adapts based on experience, recognizing patterns.
Interesting.
And Vadinsky argued for this too, having that internal learning from connectionist systems, but also having higher-level symbolic rules operating at the same time, kind of informing each other.
So you still have the logical foundation Leibniz talked about?
You can, yes. But now you add this layer of adaptability, of learning, that the purely symbolic approach struggled with. It's a richer picture.
It sounds promising, definitely. But I can imagine making these two very different approaches. Symbolic rules and connectionist learning actually work together smoothly. Must be difficult, is it?
Oh, yeah. That's a major implementation challenge. Getting the symbolic part and the connectionist part to communicate and interact effectively, that's tricky.
So how do they tackle that?
Well, one approach is something called a stratified architecture. Think of it like layers in a cake.
Okay.
You organize the system hierarchically. You might have symbolic processing happening on one layer, connectionist processing on another, but with defined ways for them to pass information back and forth. So symbolic connects to symbolic, connectionist to connectionist, but they also interact across layers.
So keeping them somewhat separate but connected.
Right. And it's important to remember, just adding a neural network doesn't automatically make it a connectionist system in this hybrid sense. The key is that the formal calculus, the rule-based part, and the adaptability, the learning part, are integrated aspects of one single cognitive system. They have to work together.
Got it. So even with these advanced architectures, it sounds like we're bumping up against those original philosophical hurdles from Leibniz again, especially around, what was it, the effectiveness and scope of representation.
Absolutely. We circle right back to fundamental questions. And a big one is the grounding problem.
The grounding problem, well, what's that about?
It's about meaning, essentially. Where does the meaning of a symbol come from? Daskal put it really well. He said most AI systems, based on symbols, fail here because the symbols they use lack the intrinsic meaning that humans attach to them.
So the symbol apple in a computer doesn't mean apple in the way it does to us.
Exactly. It's just a pattern of bits. It isn't grounded in the experience of tasting an apple or the cultural associations or personal memories. This lack of grounding makes it hard for purely symbolic or representational AI to handle things like subtle interpretation, personal meaning-making stuff Wheeler talked about.
And things like understanding context and language.
Precisely. Bedge pointed out the difficulty with semantic dynamics in context and language. Poley noted that these systems often assume concepts have fixed, static meanings. But human concepts are fluid, they depend on context. That really challenges Leibniz's idea of a universal, fixed symbolic system.
It's incredible how these deep philosophical issues persist. And you mentioned Leibniz himself was building on even older ideas, right, from mathematical logic.
Yeah, absolutely. Leibniz was partly responding to ancient Greek ideas, particularly the Pythagoreans. They believed mathematics was the key to understanding reality.
Like finding math in music.
Exactly. Expressing musical harmony with numerical ratios that showed how abstract patterns, numbers, could explain physical phenomena. And this thread runs through history, through mathematicians like Al-Khwarizmi, whose algorithms were essentially recipes for calculation.
So an AI using an equation to make a decision
is a direct descendant of that whole lineage, embodying Leibniz's ideal of computational rationality. But here's a persistent challenge. When you reduce rich concepts to abstract, numerical, or symbolic formats for computation, you often strip away the dynamic, interpreted, context-sensitive meaning.
You gain computational power, but lose nuance.
Something like that. You gain effectiveness for certain tasks, but you limit effectiveness for others that rely heavily on that richer contextual understanding. It's the grounding problem again, in a way.
Okay, so bringing it all together. These hybrid systems, combining symbolic and connectionist approaches, they seem like a definite step forward. But Leibniz's original framework, his philosophical vision, it still casts a long shadow with unresolved issues.
I think that's a fair way to put it. Systems like Clarion can reason more effectively, tackle problems beyond pure symbolic AI. That's real progress. But the philosophical challenges Leibniz wrestled with, especially around dynamic meaning, interpretation, grounding, they haven't vanished.
They just look different in modern systems.
Exactly. We need to keep re-examining those issues as we build these increasingly complex cognitive architectures. Leibniz gave us a powerful starting point, a foundational language, you could say, but we're still learning how to speak it fluently in the real world.
So it really makes you wonder, doesn't it? Well, what does this mean for the future of AI? Is genuine intelligence more about building these perfect, logical, universal systems like Leibniz dreamed of? Or is it more about embracing the messiness, the context, the interpretation, the way meaning constantly shifts and evolves for us humans? It feels like this fundamental tension born centuries ago is still right at the heart of AI research today.
It really is, and the question becomes, what kinds of new hybrid approaches might emerge? How can we build systems that are both computationally powerful and meaningfully grounded?
Will we ever truly bridge that gap between the abstract symbol and the richness of lived experience? That's maybe the billion-dollar question for AI's future. Something to think about.